two phases of a pure material to coexist in equilibrium at a fixed temperature and pressure, their Gibbs free energies must be the same. For example, at the melting point, the Gibbs free energy of the solid and the liquid phases are equal. G1 equals G2. If T and P change such that the two phases stay in coexistence, then both phases' free energies must change by the same amount. dG1 equals dG2. This is the same as writing minus S1 dt plus V1 dP equals minus S2 dt plus V2 dP. The entropies and volumes are properties of phases 1 and 2 respectively, but temperature and pressure must of course be the same in both coexisting phases. If we rearrange this equation, we can obtain an expression for the slope of the PT coexistence curve for two phases, dP dt, and that's given by the entropy difference between phases 2 and 1 divided by the volume difference between phases 2 and 1. Now, at coexistence, delta G between the two phases is 0, so delta H minus T delta S is 0, and therefore delta S is equal to delta H divided by T. Substituting this, we obtain the Clapeyron equation, which gives the slope of a coexistence line on any PT graph. dP dt equals delta H over T delta V. This is the differential form of the Clapeyron equation. It can be converted into a more directly usable expression under a couple of conditions. First, if delta H and delta V both vary little when P and T are changed, that is, they're approximately constant, then we can integrate it from some starting point on the coexistence curve, T1, P1, up to a new temperature, T2, and calculate the corresponding new coexistence pressure, P2. It's shown in this expression here. Now, because we've assumed that delta H and delta V are both constants, they can come out the front of the integral, and that simplifies the maths to give us an expression P2 equals P1, the starting pressure, plus the ratio delta H over delta V times log of T2 over T1. This equation is a good approximation for solid-liquid coexistence, melting points, as these condensed phases do not change volume much when temperature and pressure are changed. It's also a good approximation for coexistence between other types of condensed phases, different solid states or liquid crystals. Let's take an example. The normal melting point of sodium chloride is 801 degrees Celsius. What pressure would be required for the melting point to be increased to 804 degrees Celsius? The normal melting point is the temperature at which a material melts at 1 atmosphere pressure. This gives us a starting point. P1 equals 101,325 pascals, and T1 is 1074 Kelvin. We need to look up the enthalpy of fusion of sodium chloride, which is 27.95 kilojoules per mole, and somehow obtain delta V. We obtain this from the density. If the density of the solid is 2.16 grams per cubic centimetre, then its molar volume is its molar mass, 58.88 grams per mole, divided by the density, 2.16 grams per cubic centimetre. This gives 27.3 times 10 to the minus 6 cubic metres per mole, having converted the volume into SI units. For the liquid, the density of 1.549 grams per cubic centimetre gives a molar volume of 38.01 times 10 to the minus 6 cubic metres per mole. So the volume change, delta V, is 1.08 times 10 to the minus 5 cubic metres per mole. Now we just substitute everything into the Clapeyron equation, making sure that the units are consistent. This gives P2 is equal to P1, 101,325 pascals, plus the ratio delta H over delta V times log of the temperature ratio, which gives up, after all that, 7.35 times 10 to the 6 pascals, or 72.6 atmospheres. The second condition applies if delta H only is approximately constant, but we have an expression that relates temperature, pressure, and volume. We call these an equation of state. In this case, we can also integrate the Clapeyron equation from some starting point in the coexistence curve, T1, P1, up to a new temperature T2 and calculate the new coexistence pressure. But in this case, the conditions for the integral and the outcome, the final equation, are different. For example, for 1 mole of an ideal gas, we know PV equals RT, or V equals RT on P. V is not, however, constant now, but depends strongly on P and T. So for a solid gas or a liquid gas equilibrium, we also know that the volume of the gas is much greater than the volume of the solid or the liquid. This means we can approximate delta V to just the volume of the gas. In that case, we get a very different looking final expression for the coexistence between a condensed phase and an ideal gas. Starting with the Clapeyron equation in its differential form and substituting volume of the gas for delta V, then using the ideal gas expression to give us P over RT instead of 1 over V, now we can integrate that whole thing. We take delta H over R out the front of the integral because that's still a constant, and get a final expression which is called the Clausius-Clapeyron equation. Let's take an example. The normal boiling point of ethane is minus 89 degrees C. What would the boiling point of ethane be if the pressure was 10 atmospheres? Now, its enthalpy of vaporization is 14.70 kilojoules per mole. To solve this, we need to make T2 the subject in the Clausius-Clapeyron equation. That is, 1 over T2 is 1 over T1 minus R over delta H times log of the ratio of the final to the initial pressures. Substituting in our values for temperature, R and delta H, we obtain 1 over T2 is 0.00413 inverse Kelvin. If 1 over T2 is 0.00413, then T2 is 242 Kelvin. Notice that to do this calculation, we didn't have to convert pressure into pascals because the expression contains the ratio of the two pressures. As long as we use the same units, the calculation will work out just fine.